So over the past couple of sections, we've taken a good bit of time to explore bases and coordinate systems, and we've sort of put that to some work on our topics on subspaces. We're going to now turn towards eigenvalues and eigenvectors. So while this may seem unrelated, at the very end, we're going to sort of try to tie all this back together. So let's start out with the definition of an eigenvector and an eigenvalue. We're going to start out with an n by n matrix, A. We say that V is an eigenvector of A if there exists a scalar lambda so that A times V is equal to lambda times V. We call the scalar the eigenvalue associated to the eigenvector V. So while this may seem fancy and is some sort of hodgepodge of German and English, eigen being the German word that roughly means characteristic, the verbiage here amounts to saying that an eigenvector is a vector for which the action of the matrix A is easy to understand. Namely, A simply scales V by lambda. So let's consider the following matrix. And let's consider the two vectors V with entries 2, 1, and W with entries negative 1 and 2. If we multiply each of these vectors by A on the left, then we'll get 14 plus 6 in the first coordinate, which is 20, 12 minus 2 in the second coordinate, which is 10. And we can see that if we factor a 10 out of each of these, this is the same thing as 10 times V. And similarly, if we multiply W by A on the left, we'll get, and similarly, if we multiply W on the left by A, we'll get negative 7 plus 12, which is 5 in the first coordinate, and negative 6 minus 4, which is negative 10 in the second coordinate. And if we factor a negative 5 out of the top and the bottom, we'll see that we get W back. This tells us, by our definition, that V and W are both eigenvectors of A. Their eigenvalues are 10 and minus 5 respectively. Now that we have an example, the question in your mind is probably, why are we talking about this? So to get a feel for why this might be useful, let's think about diagonal matrices as a nice toy example. So diagonal matrices have the form lambda 1 times E1, lambda 2 times E2, etc., down to lambda n times En, which amounts to a matrix whose only non-zero entries are along the diagonal, and they are lambda 1, lambda 2, down to lambda n. And, as you may have guessed, the naming convention for the scalars, lambda 1, lambda 2, through lambda n, is in fact suggestive. So to get a feeling for why this should be true, let's consider an example. So let's take the matrix whose columns are 3e1 and negative e2. If we want to understand the action of this fairly small matrix on an arbitrary vector with coordinates x and y, it's easy to do so simply by just computing things. So this gives us a scaling horizontally by 3 units, as well as a reflection across the x-axis. It's easy for us, with this geometric description, to identify what our eigenvectors and their eigenvalues should be. Namely, if we take any vector that lies on the x-axis, we can write it as some scalar x times e1. When we multiply our vector xe1 by d on the left, we can use linearity to pull the scalar x through the product, and we recognize that d acting on E1 simply outputs the first column in the matrix. And so we see that any vector which lies on the x-axis is in fact an eigenvector for the matrix D, and its eigenvalue is 3. And similarly, if we choose a vector y(E2), which lies on the y-axis, playing the same sort of game, and we see that we get negative y(E2). So again, we see that y times E2 is also an eigenvector, and the eigenvalue associated to this eigenvector is negative 1. So while this may seem like a silly exercise, which doesn't get us anything beyond what was already obvious, this does give us some perspective and maybe some motivation. The important thing here is E1 and E2 are both eigenvectors for our matrix. And these two vectors are special because they form a basis for our space. So, of course, then the question is, well, why is this special? Well, once we know that we have eigenvalues and eigenvectors, and those eigenvectors form a basis, we can simply rewrite any vector in terms of our basis. If we want to apply the matrix D to our vector, well, that's the same thing as applying it to this linear combination xe1 plus ye2. And of course, linearity tells us that we can split this into the sum d multiplied by xe1 plus d multiplied by ye2. And then we can pull the scalars through. And we remember that E1 is an eigenvector with eigenvalue 3, and E2 is an eigenvector with eigenvalue minus 1, and of course, we get back to exactly the same computation that we did at the beginning. So, of course, for a diagonal matrix, okay, this is a silly operation, but the idea is that if we can do this for another matrix that is not a diagonal matrix, this actually is a time-saving device. So if we return to our first example, where we had the matrix A, whose columns were 7, 6, and 6 minus 2, A had eigenvectors V with coordinates 2 and 1, and W with coordinates minus 1 and 2. The eigenvalues were 10 for V and minus 5 for W. Now if you plot the 2 points, 2, 1, and minus 1, 2, it's easy to see that they do not lie on the same line through the origin. So the vectors v and w are clearly linearly independent. They live in a space of dimension 2, so they're a basis. So for any u in R2, there always exist scalars a and b, so that we can express u as a linear combination of v and w. Computationally, this makes multiplying a vector by a on the left much easier. If we think about our vector as being expressed in the coordinate system corresponding to our basis b, then we can write u as the vector a, b. Well, of course, now, if we think about the vector AU expressed in our new coordinates, is simply 10a minus 5b. We can think about this as the diagonal matrix 10, 0, 0 minus 5 multiplied by AB. If we call this diagonal matrix D, then we can think about this as D multiplied by U expressed in the coordinates for B. So of course, if we're willing to shift our coordinate system, then we can think about the action of our matrix on a vector as coming from diagonal matrix. And in fact, we can make this relationship a little bit more precise. We recall that we can use a matrix P whose columns are our basis vectors v and w, and p's inverse to translate between the two coordinate systems. In particular, a times u expressed in the coordinate system for b. In the standard coordinate system, we would multiply that by p. And of course, our observation above says that we can express this vector au in coordinates b as the diagonal matrix D multiplied by u expressed in the coordinates for our new basis b. And if we want to think about this expression in terms of the original vector u, we know that we can obtain the new coordinates by multiplying the vector u by p's inverse. So if we recall exercise 3 from the invertibility and bases 3 homework, this tells us that our matrix A is similar to the diagonal matrix D. So over the next few sections, we'll devote a good deal of time to understanding exactly how to find all of the eigenvalues, how to find all the eigenvectors for a matrix, and we're going to think a lot about how we can mimic the construction in this example for more general matrices.